Hey everyone, today's video is going to be just a quick review of the major theorems we've covered so far, as well as just going back over linearization and differentials briefly. So, IVT, EVT, and MVT are big theorems. Let's start with intermediate value theorem, or IVT. The conditions here, if f of x is continuous on a closed interval from A to B, and we know that m is some value between f of A and f of B, then there exists a value c between A and B such that f of c is equal to m. Right, so the big idea here is that if this function is continuous over the interval from A to B, then that function has to take on every value in between f of A and f of B. The extreme value theorem, our condition here is that if f of x is continuous on a closed interval from A to B, then f of x has both a maximum and a minimum on that interval. Oops, there we go. Now remember, if it's not continuous on that closed interval, the EVT does not apply. Now that doesn't mean that the function does not have a maximum and a minimum, it just means that we can't guarantee it using that theorem. And then our last one was the mean value theorem. This one has two major conditions. So if f of x is continuous on a closed interval from A to B, and it's differentiable on an open interval from A to B, then there exists a point, and I'm going to say a point C between A and B such that f prime of C is equal to f of B minus f of A over B minus A. So in other words, at that point, the slope of the tangent equals the slope of the secant over that interval. Okay, so those are our three big theorems. So it's important that you know the conditions. Sorry about that. The conditions of those theorems as well as what they guarantee. So from there we went on and talked about our first derivative test and our second derivative test, right? And luckily they're kind of just how they sound. The first derivative test uses the first derivative to determine whether a function has a maximum or a minimum. So the idea here is that if at a point C, f prime changes from positive to negative, so if my derivative changes from positive to negative, then f has a max at x equals c. And then it's just the reverse for a minimum. So if at a point C, f prime changes from negative to positive, then f has a minimum at x equals c. And again, this is the stuff we've been using pretty much all chapter long since we started with graph sketching. So the second derivative test was a little bit new. For the second derivative test, it looked like this. We said if f prime of c equals 0. So at some value of c, my derivative is 0, or I have a horizontal tangent. And f double prime of c is less than 0, then f has a maximum at x equals c. Right? Because really what's happening there is that we have some horizontal tangent. If f double prime of c is less than 0, then it's concave down, which means that value has a max. So for a minimum, we say if f prime of c is equal to 0 and f double prime of c is greater than 0, so now I'm concave up, then f has a minimum at x equals c. Okay, so those were all of our theorem and tests. And again, those come up a lot on the AP exam, so we want to make sure that we know how to justify those appropriately. So the next thing we talked about was linearization and differentials. And really this was all about using the tangent line to do some kind of approximation. So the linearization, let's say, can be used to approximate values for the original function using the tangent line. Right, and we said if we pick our center of linearization, if we pick points very close to that center, then the tangent line should be a good approximation of that curve. So as an example, it says use a linearization to approximate the value of square root of 26. So I'm going to need a couple things. I need a function here. And so since we're dealing with the square root, our function is the square root of x. And we need to pick a center for this linearization. So I want it to be something that's close to 26, but is also a perfect square. So 25 is going to be our option here. So remember, we said linearizations were using the tangent line. So that's the equation we need to be able to come up with. So to get the equation of the tangent line, I need a point. Well, we already said our x-coordinate is 25, and the square root of x, or square root of 25, excuse me, is just 5. So there's our point. Our slope we're going to get from the derivative, which is 1 over 2 root x. Hopefully we all have that memorized by now because we've used it so much. I should say that's f prime of x. So then I'm going to find the value when x is 25, which is going to give me 1 over 2 times square root of 25, which is just going to be 1 over 10. So now I have enough to write my equation of the tangent line. So y minus 5 equals 1/10 times x minus 25. And all we do is rearrange that to get our linearization. So my linearization is going to be 5 plus 1/10 times x minus 25. So that is the linearization. That equation is my linearization. So now we're going to use it to approximate the value of the square root of 26. All right, sorry, I had to pause that for a second, so I don't remember exactly where I left off. But the idea here is that when we come up with this equation, that is our linearization. Sorry if I'm repeating myself. And we're going to use that to approximate this value. So I know that the square root of 26 is going to be approximately equal to my linearization at 26. And here's where I use my equation. So 5 plus 1/10 times my x is 26 minus 25. So now we go ahead. That's just going to give me 5 plus 1/10. So I know that's 5.1. So I know the square root of 26 is approximately 5.1. If I were to put it in my calculator, we can see that that is a really close approximation. So that's the ideas with linearizations. We're using it to approximate the value of a function. Now, differentials, right? We said we use these to approximate the change in the value of a function resulting from a change in x. Okay, so now we want to say, hey, if x changes by a certain amount, about how much is the function itself going to change by? So delta y, this is the actual change in y. So to get that, we're using our function. So delta y was, we had our f of x plus delta x minus f of x, or really we said that's really our y2 minus our y1. Now dy, right, this is our approximated change. And this uses the tangent line. And our equation for that, for dy, remember, was f prime of x times dx. And to calculate that, we would be given the x and the change in x. So that, along with graph sketching, is what's going to be on our next quiz, and you'll have some time to review and prepare for that.